Welcome to this coding tutorial. In this session, we'll tackle LeetCode problem number 371, sum of two integers. The challenge is to compute the sum of two integers without using the plus or dash operators. We'll explore how bitwise operations can help us solve this problem in an efficient and elegant way. Let's dive in. In this problem, we need to calculate the sum of two integers, a and b, without using the addition or subtraction operators. The goal is to find an equivalent way to perform the addition operation using bitwise operations. The input consists of two integers, a and b, both of which lie in the range of -2 to the power of 31 to 2 to the power of 31 1. The output will be a single integer that represents their sum. For example, if a is 1 and b is 2, the output will be 3, as the sum of 1 and 2 is 3. This is a straightforward example to help us understand the problem requirements. Now, let's look at how we achieve this sum using bitwise operations. First, we calculate the bitwise XOR of a and b. This operation gives us the sum without accounting for the carry. For instance, 1 XOR 2 equals 3. Next, we calculate the carry by performing a bitwise AND of a and b and then left shifting the result by 1. In this example, 1 and 2, left shifted by 1 gives 0, since there are no bits to carry over. Finally, we add the results of these two steps to get the final sum, which is 3. Another example is when a is -2 and b is 3. Here, -2 XOR 3 gives -3, and the carry, calculated as -2 and 3, left shifted by 1, equals 4. After obtaining the XOR and carry values, the result of adding these two gives the final sum, which is 1 in the case of -2 and 3. Let's explore one more example. If both a and b are 0, the sum is 0. Using bitwise operations, the XOR of 0 and 0 is simply 0, and the carry, calculated as 0 and 0, left shifted by 1, is also 0. Adding these two results gives the final sum of 0. These examples demonstrate how bitwise operations can effectively mimic the addition process without directly using the plus or dash operators. It's important to note that the output will always fit within the range of a 32-bit signed integer. Let's consider some edge cases. If both numbers are 0, the output is 0. When one number is 0, the output is simply the other number. For example, if a is 5 and b is 0, the output is 5. For negative numbers, like a equals -4 and b equals -6, the result is -10. With mixed signs, such as a equals -3 and b equals 7, the result is 4. Finally, for large numbers near the 32-bit integer limits, such as a equals 2 to the power of 31 1 and b equals -1, the output is 2 to the power of 31 2. These scenarios highlight the robustness of the bitwise approach for handling a variety of inputs within the specified constraints. To solve the problem of summing two integers without using the plus or dash operators, we considered two approaches. The first is a brute force method, where we simulate addition by repeatedly incrementing one number while decrementing the other until the second number reaches 0. While this approach is straightforward, it's computationally expensive, with a time complexity of O, max, A, B, which makes it impractical for large inputs. The second approach relies on bitwise manipulation, which is much more efficient. Here, we use the XOR operation to calculate the sum of bits without considering the carry, the AND operation to identify which bits produce a carry, and a left shift to move the carry bits to the correct position for the next higher significance. These operations together mimic binary addition in hardware, making this method computationally elegant and efficient. In the bitwise manipulation approach, the process works iteratively. First, we use a (b) to calculate the sum of the two numbers without considering the carry. Next, we use a and b, 1 to compute the carry, which is then shifted left to align with the proper bit position. This process repeats until the carry becomes 0, at which point the sum is complete. The time complexity is O(1) for fixed-width integers, such as 32-bit numbers, because the number of bits limits the iterations. Space complexity is also O(1), since no additional space is required. This method is advantageous not only for its efficiency but also for its ability to handle all integer inputs seamlessly. It aligns perfectly with the properties of binary arithmetic, making it a natural fit for this problem. The realization that XOR and AND operations together replicate the behavior of binary addition was a key insight that drove our choice of this approach. One important trade-off to note is that while the bitwise manipulation approach is exponentially faster than brute force, it may initially seem less intuitive to those unfamiliar with bit-level operations. However, its efficiency and constant time performance for fixed-width integers make it the superior choice. Alternative methods, such as brute force, are simply too slow and computationally infeasible for large inputs. Other mathematical approaches, like using logarithms or more abstract number-theoretic properties, are overly complex and lack the simplicity and directness of bitwise operations. The chosen implementation also demonstrates how bitwise arithmetic can be applied effectively to solve real-world problems. By understanding how the XOR and AND operations interact, we can construct a solution that is both elegant and practical. This implementation demonstrates the power of bitwise operations in solving the problem efficiently. By iteratively calculating the sum without carry and then accounting for the carry, we mimic the process of binary addition at the hardware level. The final solution ensures that all integer inputs, whether positive or negative, are handled correctly, and it avoids the inefficiencies of alternative approaches. This method highlights the elegance and computational efficiency of leveraging bitwise arithmetic for problems that initially seem to require traditional arithmetic operators. To solve the problem of adding two integers without using the plus or dash operators, we turn to bitwise operations. These operations allow us to manipulate integers at the binary level, which is key to achieving our goal. The XOR operation, represented by caret, is central here because it mimics addition without carrying. For example, in binary addition, 1 caret 1 gives 0 since there's no sum when both bits are 1. On the other hand, 1 caret 0 or 0 caret 1 results in 1, which mirrors addition when only one bit is 1. This gives us the partial sum. Now, to handle carrying, we use the AND operation, represented by AND, which identifies where both bits are 1. These are the positions where carrying occurs. Shifting this result to the left using moves the carry to the correct position for the next bitwise addition step. Together, XOR and AND with left shift provide the tools we need to simulate integer addition bit by bit. Using these bitwise operations, we can construct an iterative approach to compute the sum. The process begins with two integers, a and b. While there's still a carry to process, which means b is not 0, we perform the following steps. First, calculate the partial sum with XOR, sum equals a caret b. This gives the addition result without considering the carry. Next, determine the carry using AND and left shift, carry equals a and b, 1. This identifies where the carry occurs and shifts it to the correct position for the next addition step. Then, update a with the partial sum and b with the carry. This effectively moves us closer to the final result. The loop continues until there's no carry left, at which point b becomes 0. At this stage, the value of a represents the final sum of the two integers, which we can return as the result. This algorithm is remarkably efficient due to its simplicity. The only data structures we use are the two integers, a and b, to store intermediate results. No additional memory is required, making this approach highly space efficient. The key operations XOR for addition without carry, and combined with left shift for carry computation, and the iterative update loop are straightforward and repeat until the carry is eliminated. In terms of complexity, the time complexity is O(1), because the number of iterations depends on the number of bits in the larger of the two integers, which is fixed for a given integer size, such as 32 bits. The space complexity is also O(1), since we only use a constant amount of space for the variables. This combination of efficiency and simplicity makes the algorithm an elegant solution to the problem. Let's walk through an example to see how the algorithm works in practice. Suppose the inputs are a equals 3 and b equals 5. In binary, this is represented as a equals 011 and b equals 101. In the first iteration, we calculate the partial sum using XOR, sum equals 011 caret 101 equals 110. This gives us the addition result without the carry. Next, we calculate the carry using AND and left shift, carry equals 011 and 101, 1 equals 0011 equals 010. We then update a to 110 and b to 010. In the second iteration, we repeat the process. The new sum is 110 caret 010 equals 100, and the new carry is 110 and 010, 1 equals 010, 1 equals 100. Updating the variables, we now have a equals 100 and b equals 100. In the third iteration, the partial sum becomes 100 caret 100 equals 000, and the carry shifts to 100 and 100, 1 is equal to 100, 1 equals 1000. This updates a to 000 and b to 1000. In the fourth iteration, the partial sum is calculated as 000 caret 1000 equals 1000, and the carry becomes 000 and 1000, 1 equals 000, 1 equals 0000. At this point, b is updated to 0000, indicating that there's no carry left to process. Since b is now 0, the loop terminates, and the value of a, which is 1000 in binary, is returned. Converting this back to decimal, the result is 8. The algorithm handles various edge cases naturally. For instance, it works seamlessly with negative numbers due to the 2's complement representation used in binary arithmetic. If either of the inputs is 0, the result will simply be the other number. The approach also handles large numbers appropriately, respecting the overflow behavior of the underlying integer representation. This robustness ensures the algorithm is reliable in a wide range of scenarios. This solution to LeetCode problem number 371, sum of two integers, performs the addition of two integers a and b without using the plus or dash operators. Instead, it relies on bitwise operations to simulate addition. Here's a detailed explanation of the code. 1. Bit mask definitions. Two constants are defined. Max is 0x7ffffff, representing the maximum positive value for a 32-bit signed integer. This value helps handle signed integers correctly. Mask is 0xFFFFFFF, a 32-bit mask used to limit operations to the lower 32 bits, ensuring correct behavior for negative numbers. 2. Iterative addition using bitwise operators. While b, representing the carry, is not 0, the algorithm continues to calculate the sum. Carry calculation, carry equals a and b, 1. The bitwise end, a and b, identifies which bits would produce a carry, and the left shift, 1, moves the carry to the correct bit position for the next calculation. Sum without carry, a equals a to the power of b, and mask. The XOR operation, a caret b, performs addition without carrying, while the mask limits the result to 32 bits. Update the carry, b equals carry and mask. The carry is masked to ensure it remains within 32 bits. 3. Result handling for signed integers. After the loop, if a is less than or equal to max, it is returned directly, as it falls within the range of positive signed integers. If a exceeds max, it represents a negative number in 32-bit signed integer arithmetic. The expression, a caret mask, converts it correctly to its negative value. This approach ensures that the addition is performed correctly for both positive and negative integers within the constraints of 32-bit signed arithmetic. The algorithm has time complexity O(1), as the number of iterations is limited by the number of bits in the inputs, 32 bits. This makes the solution efficient and suitable for competitive programming scenarios. This is the Java implementation of the sum of two integers problem, equivalent to the provided Python solution. The logic uses bitwise operations to compute the sum without using arithmetic operators. Key differences include explicit type declarations for constants and variables in Java, and the use of bitwise masks to handle 32-bit signed integer constraints. The algorithm iteratively calculates the sum and carry until no carry remains, ensuring correctness for both positive and negative integers. To solve the problem of adding two integers without using the plus or dash operators, let's walk through the first example where a equals 1 and b equals 2. Initially, their binary representations are 00014a and 00104b. In the first step, we calculate the carry using a and b, 1. The bitwise in of a and b results in 0000, and left shifting this by 1 gives carry equals 0000. Next, we update a with the XOR of a and b, followed by applying a mask. The XOR operation 0001 caret 0010 gives 0011, which corresponds to 3 in decimal. Now, we update b to the carry value masked appropriately, which remains 0000 in this case. Since b is now 0, the loop terminates, and the result is the current value of a, which is 3. This demonstrates how the algorithm handles the addition of two positive integers step by step. Now let's consider an example where we add a positive and a negative number, a equals -1 and b equals 2. The binary representation of a in 32 bits is all ones, while b is represented as 00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000The bitwise and produces 0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000w00000000 Next, we update a using the XOR of a and b, which results in 1111111111111111111111101, equivalent to -3 in decimal. Then, we set b to the carry value, which is 00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 in a and b until b becomes 0. Updating a and b until b becomes 0. After several iterations, the algorithm converges, and the final result is a equals 1. This demonstrates how the algorithm handles the addition of a positive and a negative integer while leveraging bitwise operations. For the third example, we examine the addition of two negative numbers, a equals -3 and b equals -5. Their binary representations are 11111111111111111111111111111111114a and 111111111111111111111111111111111111114b. First, we calculate the carry using a and b, 1. The AND operation results in 11111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111 1000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000. Next, we compute A as the XOR of A and B, yielding 00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 equivalent to -14 in decimal. The process repeats, with A and B being updated iteratively. Eventually, B becomes 0, and the result stabilizes at A equals -8. This example illustrates how the algorithm effectively handles the addition of two negative numbers by iteratively resolving the carry and sum using bitwise operations. The time complexity of the getSum function is O(1), meaning it operates in constant time regardless of the input values. This is because the number of iterations in the while loop is limited by the number of bits in the integers being processed. For standard 32-bit integers, the loop runs at most 32 times, once for each bit position. Within each iteration, we perform two main operations. First, the bitwise AND operation combined with a left shift calculates the carry bits, and this operation is constant time, or O(1). Second, the bitwise XOR operation calculates the sum without the carry, and the masking operation ensures we only retain the last 32 bits. Both of these are also O(1) operations. Because the number of iterations is constant, and each operation within the loop takes constant time, the overall time complexity is O(1). The space complexity of the getSum function is also O(1), meaning it requires a constant amount of memory regardless of the size of the input values. This is because the algorithm only uses a fixed set of variables, A, B, carry, max, and mask. These variables occupy a constant amount of memory, with A and B each storing 32-bit integers and carry holding intermediate values. Additionally, the implementation does not rely on any data structures like arrays, lists, or recursive function calls, which could otherwise increase memory usage. Since the memory used does not depend on the size of the inputs, the space complexity remains constant at O(1). When comparing the optimized bitwise approach to a naive or brute force method, the efficiency of this solution becomes even clearer. A naive approach to adding two integers at the bit level might involve iterating through the bits manually, handling carry propagation with loops and conditionals. This would result in O(n) time complexity, where n is the number of bits in the integers. For standard 32-bit integers, this would mean 32 iterations, making it less efficient than the current solution. In contrast, the optimized solution uses bitwise operations like AND, XOR, and left shift to handle carry propagation and addition in constant time. This eliminates the need for iterative carry handling and significantly improves performance, especially for larger integers or systems where integer operations are frequent. The constant time complexity of the getSum function can be mathematically justified. The while loop runs for at most 32 iterations when working with 32-bit integers, as the carry bit shifts left and eventually becomes 0. This fixed number of iterations leads to an O(1) time complexity. Each operation inside the loop, such as bitwise and XOR, left shift, and masking, is performed in constant time, further reinforcing the constant time complexity. On the space side, memory usage remains fixed at O(1) since no extra memory is allocated based on input size. Looking at best, average, and worst-case scenarios, the function consistently performs in O(1) time. For instance, if b is already 0, the loop exits immediately in the best case. In the average case, random inputs still lead to a constant number of iterations, and even in the worst case, with the maximum of 32 iterations, the time complexity remains O(1). This consistency highlights the efficiency of the algorithm. To summarize, the getSum function is an extremely efficient solution for adding two integers without using the plus or dash operators. It achieves constant time and space complexity, O(1), through the use of bitwise operations like AND, XOR, and left shift. This approach not only minimizes computational overhead but also avoids the need for additional memory structures, making it highly space efficient. These properties make the function particularly well-suited for systems with strict performance requirements or scenarios where addition operations are performed frequently. By leveraging these optimizations, the getSum function represents a significant improvement over naive methods, both in terms of time and space efficiency. When working with bit manipulation to solve problems like adding two integers, there are a few common mistakes to watch out for. First, remember that signed integers in most systems have a fixed range, such as -2 to the power of 31 to 2^31-1 for 32-bit integers. If you don't handle carry bits properly, this can lead to overflow or even infinite loops. For instance, if you're working with values like a equals -1 and b equals 1, failing to manage the carry correctly might cause your solution to get stuck in a loop. Speaking of infinite loops, another frequent issue arises when the carry isn't updated properly. If you don't ensure the carry eventually becomes 0, your loop will never terminate. Another area where errors creep in is misunderstanding the roles of XOR and AND. XOR is used to calculate the sum without the carry, while AND identifies the carry bits. You must also shift the carry left by 1 bit to propagate it correctly. Finally, watch out for unnecessary base case handling. Some solutions explicitly check if A or B is 0, but the iterative approach naturally terminates when one operand becomes 0, so these checks are redundant and add unnecessary complexity. Now, let's talk about edge cases and interview-specific insights. Testing edge cases is critical to ensure your solution is robust. For example, scenarios like A equals int_max and B equals 1, A equals int_min and B equals -1, or even A equals 0 and B equals 0 can often expose overlooked bugs. Thorough testing for signed integers and zero values is a must. From an interview perspective, understanding the core of this problem is key. This challenge isn't just about adding numbers without arithmetic operators, it's about demonstrating your grasp of bitwise operations and low-level computation. XOR and AND are at the heart of the solution, and recognizing how they work together is essential. Additionally, pattern recognition can give you an edge. Problems that restrict arithmetic operators often have solutions rooted in bitwise logic, so identifying this pattern quickly will help you tackle similar challenges. Interviewers might also dive deeper, asking you to explain why bit manipulation can be faster than traditional arithmetic in some systems. Be prepared to discuss this, as well as potential extensions like handling unsigned integers or other data types. These discussions allow you to showcase your depth of understanding and adaptability. Finally, let's look at some related problems and alternative approaches. There are several LeetCode problems that build on similar concepts. For instance, problem number 191, number of 1 bits, focuses on counting set bits, which heavily relies on bit manipulation. Problem number 338, counting bits, is about recognizing patterns in bit representation. Then there's problem number 29, divide two integers, which also restricts arithmetic operators, and problem number 260, single number 3, where XOR is used to identify unique elements in an array. These problems can help you deepen your understanding of bitwise operations. When it comes to alternative approaches, you might consider a recursive solution. This method still uses XOR and but replaces the iterative loop with recursion. While it's easier to write, it's less efficient due to function call overhead and the risk of stack overflow with large inputs. Another option is simulating binary addition manually with loops. This involves propagating carry bit by bit without relying on XOR and AND. However, this approach tends to be verbose, error-prone, and less practical for real-world use cases. These alternatives are great for learning but may not be optimal in an interview setting, so weigh the trade-offs carefully. Great work! We've successfully reviewed and solved LeetCode problem number 371, sum of two integers, using bitwise operations. Remember the key concepts of XOR for addition and with left shift for carry propagation. These techniques are not just useful for this problem but also for many other bitwise manipulation tasks. Thanks for watching, and don't forget to like and subscribe for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!